So in this video, we're going to talk about the basics of capacitance and how we can calculate it for a simple case of a parallel plate capacitor. So to start, we want to just talk about what is capacitance. So capacitance, capital C, is going to be a measure of an object's capacity to store charge. So it's a very well-named quantity because it's literally just how good is this thing at storing charge. But how much charge it can store will depend on the voltage that we apply. So we're going to talk about that phrase for a second. So let me go ahead and first write down the official definition of capacitance, which is charge per volt, which is going to be Q over delta V, some voltage difference applied across your object. So let's talk about what it means for a voltage difference to be applied. So if we go back to our previous modules, we can have that this is the voltage difference applied. We really want to visualize and think about what this means in order to understand not just capacitance, but some of our future modules related to circuits as well. So when we've applied a voltage difference, if we think back to how we've made the analogy of voltage to the idea of these contour lines of the earth, right? It's very similar to the idea of the height. We'd have these equipotential surfaces that you can view as being at different energies, right? So each voltage is a different energy per charge, and each height was a different energy per mass. Right? Different floors of the building or different voltage equipotential layers that you would have. So when you've applied a voltage difference, you've essentially created a hill between your plus V up at some top and then some minus V. You're applying a hill that then your charges are going to navigate. Remember that we have, for the positive voltage, we're going to have our positive charges like to go downhill and our negative charges like to go uphill. But either way, we're going to be giving our charges a way to move from one surface to the other. So depending on the steepness of this hill, that is how much voltage you've applied, then you're going to either collect more charges or less charges. But it's not just based on the hill, it's also based on the geometry of the material. And that's where capacitance comes in, because not everything at the same voltage will store the same amount of charge. So if we come down here, then we can see, and we can say that like for some fixed delta V, different objects store different amounts of charge. And that just has to do with the nature of the geometry as we're going to see. So there's different capacitances for different objects. And it's going to then be calculated by knowing the relationship between Q and V. So let me go ahead and mark this very important definition of capacitance, and we're going to see how it applies to a parallel plate capacitor. So if we come down here, we can look at a parallel plate capacitor. And a parallel plate capacitor has a simple geometry that it's two parallel plates, as the name implies, that are separated by some distance d, and they each have some area A. Now, in order to calculate the capacitance equation, we do want to assume infinite plates. So here we need to note that we're going to assume these plates are infinite, so we can use the equation that we have prior, which is the electric field from one plate is equal to sigma over 2 epsilon naught. We want to use that result because it's a nice simple result saying that we have this uniform electric field from each of these infinite plates. But that means that we're making this very important assumption that our area value is going to be, in this case, much, much larger, right, than D. So one way to think about that, is that we have a very, very, very large capacitor, and they're very a large sheet, and they're very close together. And so then we can use this model of them being infinite. So in that case, we can go ahead and look at the charges from, say, a positive plate on the left. Which one you make positive and negative won't matter. And those charges are going to create this electric field everywhere in space, right? And it's a uniform electric field that it's creating everywhere in space. And it will have a magnitude equal to sigma over 2 epsilon naught. On the negative side, then our plate is going to have the electric field lines go towards it. So it's going to have the electric field lines point towards it. And again, it's uniform in all areas in space. And so we can see then in this scenario that what happens is outside of the capacitor plates, that the net electric field is 0. So E net is equal to 0 outside of these plates. And that inside, we're going to have that the net electric field inside is equal to double this electric field from 1. So it's going to be equal to 2 sigma over 2 epsilon naught. And so that's just going to be equal to sigma over epsilon naught. So we know our electric field inside. And then you're probably thinking, why is she doing this? Because we're talking about capacitance. Well, remember that to talk about capacitance, if we kind of take a step back, our goal to get our capacitance, we need the relationship between charge and delta V. So there's some relationship between delta V. Prior, we used to calculate delta V given some charge. Now we're just basically trying to get that expression for our delta V in terms of charge, and then use that to look to see what the capacitance is. So we need this relationship between delta V, and remember delta V, we can get this from knowing our electric field. So if we know the electric field, we have this equation that delta V equals negative the integral of E dot dl, right? So we can find our potential from our electric field. Okay, so that's why we were finding the electric field. We're visualizing the situation. There's some electric field that's created between these charge plates. Now we want to go ahead and talk about the potential that is between these plates. So given some charge density, sigma, on each plate, right, then we want to know what is delta V between those plates. So we just found that the E is going to be equal to our sigma over epsilon naught. And recall that it's a uniform E, so that we can look at this integral and we can say, okay, then delta V is simply going to be equal to, and we're really with capacitance just dealing with magnitudes here. So I can say, okay, I'm going to ignore that negative sign because it doesn't really matter which way I go. We're looking at a value of capacitance. So the delta V then can be equal to my E, and it's uniform and it's parallel to some D vector And so that's just going to be equal to E times D. And again, I'm just talking about magnitudes here. So that's what happened to my negative sign. And so I get this very simple result, which we have seen before when we have done our module on potential, which is that delta V across the plates can be written as our electric field, sigma times D over epsilon naught. So sigma D over epsilon naught, great. Now, where's the charge in that? Remember that it's sigma that has our charge. And now that sigma used to be the charge density on an infinite plate. And so these plates are being modeled as infinite, but we're also giving them an area, assuming that area is very, very bigger than, much bigger than D. So what we can write this as is Q over A, because that's our charge per area, times D over epsilon naught. Awesome. So I am simply going to rewrite this result. I'm just going to write it here. I'm going to write it as delta V equals QD over epsilon naught A. And so if I do this, this is how we get capacitance from this. We want to remember that capacitance is equal to your delta is your Q over your delta V. How much charge per volt can you hold? And so all we do is rearrange this expression for delta V to get our C. So that's going to be the plan here. And so what we can do is we can see that our capacitance, which is Q over delta V, is simply going to be equal to epsilon naught A over D. And so a couple things to note about this, are that this is actually independent of anything except for the geometry of the object. So very importantly, we note that this is a property of the object it's dependent on its geometry only. What is the area of the plates? How far apart are they? And that might be surprising because this original equation for capacitance seems like capacitance would depend on Q and delta V, but it doesn't. What it says is basically, if we kind of zoom out at this whole picture, how steep my hill is, right? I have this picture for the hill. How steep that hill is dictates how much charge I get. So the charge is going to depend on the hill. The Q depends on V. So when you find that relationship between Q and V, they cancel out, and you end up with something that is independent of Q or V. So it is a property of the object, and it depends on the geometry of the object itself. So capacitance, again, is a measure of an object's capacity to store charge. And it is, again, very simply a property of the object. And you're going to find this for all different capacitors that you calculate the capacitance of. And in order to calculate capacitance, you just find the relationship between Q and delta V. And you're going to find that relationship is a constant and a property of the object, independent of anything but the object's geometry. So something just has a capacitance. And then the last thing I will mention is that in a future video, we're going to add a small nuance to this, and we're going to add a kappa. So the kappa is going to be what's called a dielectric constant. This example was done for a parallel plate where we had free space, just vacuum in between the plates. But we're going to see what happens when we put something that's not a vacuum in between the plates, some other material called a dielectric. Okay, so I hope that this helped introduce the idea of capacitance, and we'll keep talking about it for the rest of this module.